Okay. All right. Thank you. So I'm going to talk about a very simple problem in geometric topology, which turns out to have a lot of basic applications in computer graphics. And I think the moral of the talk is that many of the things we do in low dimensional topology, if you connect them to people who are thinking about surfaces and three manifolds and applications, you'll see that there's a lot of techniques that we know about that could be of interest. And the problem I'll talk about today is just about how to triangulate a surface. So we all know how to triangulate, we all know that you can triangulate surfaces, but the problem is in computer graphics, when you triangulate a surface, the quality of the triangulation is very important. So by, by quality of a triangulation, we mean how good the triangles are. So a good quality triangulation is one where all the triangles look roughly equilateral. The triangulation here at the left would be an example of one. And a poor quality triangulation would be one where one of the angles is. So if you think about it, there are two ways that can happen. Either a vertex can come down and sit near an edge, or one of the edges could get very short. So those types of triangles in computer graphics are called slivers, and they're bad for representing surfaces for many reasons. And this comes up in many applied math problems that you simulate you model a surface and you want to avoid these slivers. For example, if you're modeling airflow over a surface, these sliver triangles are very bad for numerics of PDEs that model dynamic fluid dynamics. So this very basic problem is, given a surface, for example, this sphere, how would you find the triangulation with all the triangles as close to equilateral as possible? So here's I'm going to show you an example I'm going to show you a method of doing this, which was joint work of myself and Maria Trinkova at UC Davis, something we worked on over the last couple of years. And this is an actual application of our algorithm. It's actually implemented in software, the algorithm we've developed. And this is an example of a surface which is modeled. It's a standard example in computer graphics. It's a dragon. And it's got about 850,000 triangles forming this surface. And at the left is the standard model, which is circulated by the computer graphics community. And you can see it's sort of got this modeled pattern on it. On the right is the output of our algorithm, which is triangulated with much nicer triangles. And you could, in the old days, those of us who had CRT TVs, when you got a bad channel, you got all this random noise on the screen. And that's sort of what the pattern looks like on the left. There's a lot of random noise because the triangles have all kinds of shapes. Whereas on the right, you see it's much more evenly shaded because the triangles are much more regular. So this algorithm actually is not just a theoretical algorithm. It's actually implemented in practice and quite effective in real examples. And it's based on some methods of low-dimensional topology that you're all familiar with. So I want to show you how this goes. So the basic problem is, given a surface in 3 space, how close to equilateral can we make the angles of the triangulation? So there's a purely mathematical problem. We have a 2-dimensional surface of some genus and a Riemannian metric. Can you find some triangulation with the angles as far away from 0 as possible? And if you think about it, in a general surface, you have to have, depending on the Euler characteristic, unless it's a torus, you're going to have an angle of, you're going to have a vertex that doesn't have valence 6. So you're going to have, for general surfaces, either at least one valence 5 or valence 7 vertex, depending on the Euler characteristic. So by Gauss-Bonnet, the best you can do is get something a little worse than 2 pi over 7 to 2 pi over 5. That would be the best you could possibly do in a triangulation. And it turns out that that actually we don't quite do that. So what we do is we're going to give an algorithm based on normal surface theory, which gives all the triangles in the interval 35.2 to 101.5 degrees. So the smallest angle is going to be above 35 degrees, which is not bad at all for computer graphics purposes. It's a long way away from 0. So just to compare that with the previous results, the algorithm that's in common usage gives angles between 30 degrees and 120 degrees. So that's not quite as good. And it's also quite a bit slower. So the algorithm we're going to give, which is called the grad normal algorithm, is very fast in practice. It's quite a bit faster than Chu's algorithm, which is based on Delaunay triangulations, which I won't discuss today. There's another method of Lebel and Shewchuk, which is called isosurface stuffing. This actually fills up the interior with tetrahedra and gives boundary angles between 16 and 145 degrees. Not as good as ours, or even as not as good as Chu's, but it's extremely fast. And actually, our algorithms has a lot of similarity with the Lebel and Shewchuk algorithm. It gives better angles, but it runs at the same speed. So they're both. So this algorithm and ours are quite fast. And finally, I should mention an important paper which actually was completely unknown to the computer graphics community. They were quite surprised to hear about this. There's a paper by Colin de Verdier and Marin, which shows that in theory you can always find a triangulation that's arbitrarily close to the optimal possible angle given by Gauss-Bonnet. But this is not this. There is a triangulation, so this is an existence theorem, but there's no algorithm for finding it. It's not been implemented as a particular procedure to construct such a triangulation. It's based on the uniformization theorem, on the fact that you can essentially find the conformally equivalent metric, which is constant curvature, and then you can try to construct these triangulations on these constant curvature surfaces and then move them over to the original surface. So let me say a little bit about how this algorithm works. So there's two ways that we get surfaces in applications. Well, two main ways. One is we might get the surface as the level set of a function. So the function, for example, x squared plus y squared plus z squared minus 4 has the sphere of radius 2 as the level set. And you can input that function into the algorithm and it will produce this, this triangulation at the right. And in fact, that was produced by the algorithm. And if you look, I don't know if you can see it on your screen, but those triangles are very close to equilateral, most of them. And the theorem says that you'll always get, if you take sufficiently fine triangulation, you'll get angles inside this range. Of course, if you took a very rough triangulation, you might not be able to do that. And the second way you get a surface in applications is somebody gives you a mesh. So somebody gives you a piecewise linear triangulation. So if you already have a triangulation, why do you want to get a new triangulation? Well, the triangulation you're given might be turned out from might come out of a scanner of some sort, a laser scanner or a CAT scan, and they produce triangulated surfaces, but they tend to be terrible triangles. They have lots of these slivers in them. The output of, uh, of standard triangulation routines is terrible. So you want to retriangulate to get good types of triangles, triangles with no small angles, and get rid of the sliver triangles. So the standard example for this is called the Stanford bunny. It's on the left. This was an early scan of a toy bunny that was done at a Stanford graphics lab. And the triangles in this bunny have angles as low as half a degree. And so this is a standard test case for a triangulation scheme. And when we do this, we'll get vastly improved triangulation. So if you notice, there's a little region at the bottom of the left ear, which I've circled. So I'm going to zoom in on that to show you what happens for this example. So you can see that at the base of the ear there, some of those triangles at the left, the original bunny triangles, are very poor. And on the right, you see the output of the grad normal algorithm. And I'm going to zoom in one more time. And you'll see that the input triangles have some very poor angles, and they're not a very regular structure, whereas the output is quite regular and has no small angles. So one important thing to do, to realize, if you're a mathematician thinking about approximation, is that we want smooth approximation, or C1 approximation. So think of this purple surface F here. You can actually approximate F using entirely equilateral triangles, exactly 60-degree triangles, if you allow yourself to just stack pyramids of this type near the surface. So this method actually goes back to Whitney. He used it for some triangular approximation schemes, although he wasn't so concerned about meshes. But this does not give a very good approximation from the point of view of applications we're looking for. We want a C1 algorithm, a approximation algorithm. And we can just, one way to think about it is we can require that the vertices of these approximating triangles lie on the surface. So this one would not be a good approximation. Okay, so let me tell you about the standard method that's used. So this is what's used, for example, in ultrasound machines and MRI machines when they reconstruct the outlines of organs in medical scans and so on. So what they'll do is, I'm going to just illustrate this one dimension down. So there's this blue curve, which you'd like to triangulate. So in this case, you'd like to fit a polygon to this blue curve. And there's a method called marching tetrahedra, which does this. And what it does is it simply produces the normal curve that approximates the surface, or the normal surface in 3D. But it puts the vertices of this curve at the same place as where the blue curve intersects the triangles. So all I've done is taken an arc inside a triangle and replaced it with a straight line for each triangle. Now you might wonder, what if the curve intersects multiple times and so on? But then, yeah, so don't worry about that for this purpose. Let's just assume that the curve intersects a triangle and at most one arc. Otherwise, you have to get into questions about subdivision and so on, which are just not important for what we're doing now. So this is the method of marching tetrahedron, which was discovered in the I think in the 70s, and has 20,000 citations in marching cubes and marching tetrahedra. These two methods are extremely highly cited methods and widely used in computer graphics. And the drawback of them is that they tend to produce very small angles. So you can sort of see that here. Even in 1D, it produces very sharp bends in the curve. And in 3D, the same sort of thing. If you have a surface that cuts across a tetrahedra and meets edges as shown here, then you'll get some, what we would think of as a normal triangle that has very small angles. So this method is used widely, but then it needs a lot of retriangulation procedures to get rid of these small angles. So that's the existing technology. We just make a somewhat minor change to this to increase the angle quality. So we're going to produce an approximating curve to this blue curve in 2 steps. So step 1 is, rather than taking an inscribed polygon to this blue curve, we'll just pick an approximating normal curve that intersects each edge in the midpoint of the triangle vertices. So this is, if those of you who have studied normal surfaces, this is the way you would standardly construct a normal curve or a normal surface. You put the vertices at the midpoints. So this is not giving us the C1 approximation we want, but it gives a C0 approximation, and the angles are good. It can't have very sharp angles now. And then as a second step, we take these vertices, these midpoint vertices, and project them down to the closest point on F. We take the closest point projection. So now we get an inscribed curve. It's not the same as the one that you get by taking the inscribed point along the edges. And it turns out that these angles are much better behaved. So that's the basic difference between the old and new approaches. The old approach just takes vertices where a curve intersects triangle edges and constructs the corresponding polygon. And this new approach takes the midpoint edges and then does a closest point projection. Now, in dimension 3, there's going to be an extra step, which I'll talk about later. So now I want to move to dimension 3. So what we're going to do is take some surface, which is described either as the level set of a function on R3 or as a mesh, a mesh that's given us, and we're going to construct a new mesh, a new PL triangulation with good angles. So on the left, I've taken some output from step 1 of our algorithm. So step 1 is you take this surface, and let's say we're given a function on R3, and the 0 level set is what we want to approximate, what we want to triangulate or approximate by triangles. So if you look at that tetrahedra on the left, we're looking for the 0 set. Some of the vertices will have positive values and some will have negative values. So some will be on one side of the surface and some will be on the other side. So we construct the normal triangles with midpoints, or if it's if there's 2 vertices on one side and 2 on the other side, we construct the normal quadrilateral, and then we just take the union of all those. After tiling space with tetrahedra, we take the union of all those, and the kind of surfaces you get are shown on the right there. Those are what normal surfaces really look like in R3. For a round sphere, and then for a surface of genus 2. So given a tetrahedral tiling that fills up space, we can get a normal surface of this type. And the question becomes what tetrahedral tiling we can use. It turns out there's many ways to tile 3 space, and we did an extensive exploration of the whole space. And it turns out there's something called the Somerville tiling, which was discovered in 1923, and it's part of a family of tilings which was discovered by Goldberg in 1974. There's an interesting story about tiling R3 by tetrahedra. And we found that this particular Somerville tiling is the best one to use. It gives the best angles. And we explored the whole space of possible tilings and showed that no other tiling can give an improvement for the method that I'm going to talk about. So let's see this three-dimensional algorithm in practice. We have this blue surface. Step 1 is you project to the mid-normal, to a mid-normal mesh, the red surface whose vertices lie halfway along the edges of these tetrahedra. And at right you see a bunch of tetrahedra, and these red normal triangles fit together to form some sort of surface in R3, which is triangulated. And if you look at it globally, you'll get out these types of surfaces. But these aren't what we want. Their vertices don't lie on the surface. They just lie somewhere near the surface. So then we do a projection step where we project these triangles onto the surface. So this is why this algorithm is called grad normal. We use the gradient to estimate where the surface is and project down to it. So that gives us a closest point projection. And now we get a triangulation whose vertices actually lie on the surface. And here's a picture of an actual triangulation that comes up like that. And it's very disappointing. You see that some of the vertices have quite small angles. Some of the angles are quite small. We were hoping to get near equilateral triangles, and this process turns out to produce angles that are arbitrarily close to zero. However, if you look at this picture for a while, you see that all the bad angles occur somewhere on the boundary of a quadrilateral, of a vertex that has vertex 4. So we add an additional step here. Whenever we see a vertex of valence 4, we remove it and replace it. So now we have a quadrilateral, and now we add a diagonal. So I've done that to all the vertex 4 triangles. All the vertex 4 vertices have been removed at the left and replaced by quadrilaterals with an added diagonal. And now you'll see that all the angles look good. And in fact, that's not an accident. We were able to establish in the theorem that when you do these 3 steps, then all the angles lie in this interval of 35 to 101 degrees. So I'll put again the comparison to before. The best provable result before was Paul True's result of 30 and 120. So we've narrowed the angle interval around 60 to 35 to 120. And here's a table showing how this works in practice. In fact, it's not just theoretical. When you do this at various resolutions, so depending on how many tetrahedra you use to tile tree containing these surfaces, you see it converges quite quickly to the upper and lower angles converge quite quickly to these bounds that are the theoretical limit. And these computations were all done on a Mac laptop. This is actually a very fast method of computing triangulations. Let me say a little bit about how it works for mesh inputs. So here, instead of having a function whose level set we're looking at, the input is a piecewise linear surface, and we can compare the triangulation we get to the original one for the Stanford bunny. So this is just a histogram of angles, and the lesson from this is that the original bunny had a lot of angles near 90 degrees and near around 36 degrees, whereas the angles from this algorithm are much more clustered around 60 degrees. Let me take 2 minutes to indicate how something like this is proven. The idea is for these normal surfaces with midpoints, you can compute the angles very easily. They're just functions of these particular tetrahedral shapes we used. When you have a surface cutting across a tetrahedra, you can measure how much angle distortion there is depending on what angle you project to the surface. So what you have to do is look at all possible normal disk types and all possible projections. A projection corresponds to a point on the plane, the direction in which you're projecting to. And the idea is I'm not going to give anything sort of a very rough overview of this proof, is that you just have to analyze all the different ways you can project and you'll see that you'll get a function on the sphere, collection of functions on the sphere actually, corresponding to different ways to project. And the worst cases turn out to be on the boundary of these regions. So the worst angle distortions happen on the boundary of these spherical regions. And you can parameterize these spherical regions and just compute how bad the angle distortions are and what the smallest and largest possible angles you can get are. And you get all these different cases. There's 24 cases here, but they actually represent a lot of duplications. And so we did this. This kind of graph was actually done in Mathematica, and shows that the worst angle is 101 degree, and the largest and the smallest is 35 degrees. And this has actually been implemented in Python, and it's available if you want to. If any of you want to triangulate a surface, you can find the software there, and do it for quite complicated surfaces. So, thank you for watching.
Okay, thank you for a lovely presentation here. Are there questions? Okay, I guess we will reconvene then in about 10 minutes.